Hello there. Welcome to this presentation on understanding subharmonics. My name is Joe Perez. My contact information is in front of your screen, just in case you have any other questions after this presentation is over. So what I'm going to do is I'm going to start by talking about a real event that happened somewhere in North America, and it caused damage to the equipment due to subharmonics. So this is the system 1 line that we'll be referring to, and what we got here is we got some generators, about 6 generators, which at the time of the event they were loaded. Only generation 6 was loaded, providing about 45 MVA, and we also had wind farm generation, and it was providing about 15 megawatts, 15 loaded at 15 MVA. The particular switching station connects with our substation on the left hand side, and on this 345 kV line we have a series line capacitor, and on this series line capacitor we have bypass switch or breaker that allows the capacitor to be isolated. To the right hand side of this 1 line we have left field substation, which is interconnected by a 345 kV line. So the sequence of events is started by putting the series capacitor, inserting the series capacitor, then the loading of each generation, 45 kV for the 6 generator 6, and about 15 megawatts for the wind line. So at 8:15, at 8:17:32, both breakers are opened on Lakefield substation in order to isolate the 345 kV line. Next, at 8:17:38, the protective relays on the generators operate, and breakers AS31 and AS33 are open to isolate the entire generation station. Now, in order to isolate the rest of the kV, the rest of the line, breaker AS32 is also open, and when this is isolated, the bypass capacitor breaker is also open automatically. Now, in order to re-energize the system again, breaker AS31 is put back in service, and what happens next is at 10:50 AM particular relay is operated, and the breaker AS31 is stripped back open. Well, it is found that there is damage at the 4 kV bus in generator 1, and what was known was that there was a flashover on the generator bus. Now there's many different reasons why there would be a flashover. One of them is pretty much overvoltage. When overvoltage occurs, the insulation breaks down, and the insulation is no longer able to insulate the potential difference. This is a recording of the generator voltage, and this is in per unit values. So we can see that this was operating at 0.18 per unit, and all of a sudden it escalated rapidly. The next trace here are the currents and voltages captured by the Tesla 3000 DFR. And what we can see on these traces is that these currents do not look sinusoidal. So we have a lot of non-sinusoidal curves on these currents, and this needs to be investigated. So if you have a series line capacitor, if you have a generator or wind farm in your system, and you see something like this, it should immediately provoke some attention to investigate what the causes are, or why the signals look this way. Now, for this scenario, we extracted all the frequencies that were embedded into the signal, and found out that there is a lot of branches of subharmonics. So this is just a good start to begin this presentation of subharmonics. This gives you an idea of what subharmonics can do, how subharmonics look like, and now we'll talk about the concepts of subharmonics. Now, many of you might or might not know what a subharmonic is, but to start with, let's talk about regular harmonics, which are the harmonics composed of multiples of the fundamental, and these are usually caused by non-linear loads such as air conditionings or inductors or any other type of equipment that would cause the current to withdraw in a non-sinusoidal way. So these loads draw currents that are not pure sine waves. So they're pushing or they're pulling current in a strange manner that causes the frequencies to be embedded as 120, 180, 240, etc. Now, when you have a capacitor, a resistor, and an inductor in series, voltages and currents with frequencies below the fundamental, such as the 25, 23, 30, etc., would also be created. So these currents are being pulled in a different manner, not in an exact sinusoidal way. So the subharmonic is defined as this formula that you see in front of your screen, with pretty much the fundamental frequency multiplied by the square root of the capacitor reactance divided by the sum of the generator plus the electrical system and plus the transformer reactances. And that's how the subharmonic for a particular system can be calculated. Now, the subharmonic in a system usually interacts with the system that exists and coexists with the system in a regular manner. Now, the generator armature subharmonic currents that are in the system, if these generator currents usually are very, very small, so the currents are very small, which do not cause very much problems. Usually these subharmonics are overdamped by the system. But when these subharmonics interact with the armature of the generator, these currents produce other magnetic fields with frequencies below the fundamental, which are the FER or subharmonic frequency. And these currents, or subharmonic currents, are induced in the generator rotor, so they are transposed due to the magnetic field into the generator rotor. As a result, these currents produce another frequency in the rotor, which is calculated as the subtraction between the fundamental frequency minus the subharmonic frequency, and therefore we have the rotor frequency. As a result, this new added rotor frequency results in new armature voltages because the rotor is rotating, and as a result, this rotation produces another magnetic field which sends it back to the system. Subharmonic currents, and if this usually can produce generator self-excitation. Now, because the rotor is turning faster than the subharmonic armature currents with frequency R, there's a slip created which simulates the induction motor or induction machine. Now, why do we say that it produces a slip? Well, because the new frequencies are not rotating at the same frequency that the fundamental frequency currents are rotating, and that is the reason why this new subharmonics produce the slip. Now, the slip can easily be calculated as the subtraction between the subharmonic current minus the fundamental divided by the subharmonic current. And as we can see here, the subharmonics are always going to be less than the fundamental. And on this subtraction, we know that the slip is always going to be negative, which results in a negative resistance according to the graph that we're seeing here on your screen. Now, R prime is the rotor resistance. Now, we know that the rotor resistance will depend on the speed of the generator, and the speed, as we know, has that slip inserted on it. So the rotor resistance will always be negative. Now, what happens is that if the rotor resistance is always negative, the damping effect will always be negative. So as a result, if the series compensation is very high, the slip will be very small, and therefore R will be a negative large number. We also know that the resistance of the system acts as a damping effect. In other words, the subharmonics can be damped out by the amount of resistance we have in the system. So if this negative, if the addition of the damping resistance or in the resistance of the system is negative, so if we are adding the resistance of this rotor in the resistance of the system, and the addition becomes negative, then we know that there's not going to be enough damping in the system to get rid of those subharmonics, and as a result, they're going to get magnified. So your voltages and currents are going to produce growing oscillations, which may build up to the very dangerous high values. So, in order to emphasize this concept better, understandably these concepts are not very simple to understand, but an example of this might clarify what that means. So what we have here is a system line of this circuit, and we have a generator, a transformer, we have the series compensation, and then we have a load. So taking this data, we can calculate the subharmonic frequency, and for this system we have a subharmonic frequency of 36 Hz. Now we can also calculate the slip. Now the slip is your subharmonic minus your fundamental, which will give you a negative number of 0.66 per unit. And now with the slip in our hands, we can calculate the rotor resistance. Now the rotor resistance for this particular circuit becomes a negative number of negative 0.0057 per unit. So we know that we need to add the rotor resistance and the network resistance, and if this value is negative, then we will expect growing oscillations. So adding the rotor resistance and the network resistance will come out to a value of a negative number of 0.0037 per unit. So we know that the addition is negative, and as a result we can expect increased subharmonic oscillation, or the subharmonics are going to just produce a resonant effect that is just going to keep building up, and produce magnification of voltages and currents. So using MATLAB to simulate the subharmonic effect, what we have here is a generator. On the left hand side we have a transformer, we have a breaker, a transmission line, and then we also have series compensated series capacitor, and we have another breaker, we have those two there, and then we have another system there which also has a series capacitor in another transmission line. So if we put a single line to ground fault on the system, a bus 1, if we put a line to ground fault on the transmission line shown there with the red breaker fault, and we see the response at bus 1. This is what the simulation gives us now. The voltages are the traces on the top, and the currents are the traces on the bottom. Now, for the currents, we can see that there is some oscillations going on, but however they remain stable. They don't grow. Eventually the resistance of the network will damp out the oscillations, and the system will come back to normal. Now, for the frequency versus impedance graph, here we have a subharmonic oscillation based on the 11th harmonic. So we know that the highest subharmonic is going to be on the 11th harmonic range. So the same fault event, but in this case seen at box 2. Now again we see the high current going up, however the currents remain stable, even though there are some subharmonic oscillations going on at the same time. Now, using the same system, however for this case, let's put a 3-phase fault seen at box 1. Now we can see that the voltages have dramatically increased, and if we look at the per unit values there, usually the system, for this case the system starts at 1 per unit, and then you have the fault, and exponentially it increased, so that at 0.7 seconds our per unit value for this voltage has increased to 2 per unit. So that is an excessive amount of voltage, and such excessive amount of voltage is going to break down the insulation, and we can see that this type of voltage does not stop there. It increases as time increases. Now for the voltages, for the currents, we have the oscillations as well, but they don't increase exponentially. For the same event, but in this case seeing bonds 2, we have the same example, we have the same result. The voltages increase exponentially, reaching about 2 per unit about 0.7 seconds. And for the currents, we can also see that the currents increase in this case, but in a slow rate. So the increase rate for the currents is a little bit slower, but for the voltages, it's extremely high. So this is a simulation of how subharmonics can affect your system. So for the companies out there that are trying to understand how subharmonics can affect your system, well, a subharmonic effect can also have an overvoltage condition, and this is what's called the induction generator effect. Because of the slip, it simulates the induction generator. Now it can also produce this is the frequency versus impedance for the second event. Now, talking about the effect of net resistance on the system. Now, for this case, I have increased the line resistance in my lab, and we know that the net resistance now is positive. Now, when the net resistance is positive, now we know that this system is not going to have ground oscillations. However, we can see that subharmonics are still present because of the traces tell us that. Now, you can extract all the frequencies, and you can pretty much tell what kind of frequencies they are, but we know these frequencies will be damped out by the resistance of the circuit or the network. So that is the effect of what the net resistance has in the system. The same effect is seen as at both 2, so no growing oscillations, which is good. So this is how subharmonics can affect your system. Now, we also know that subharmonics can produce torsional interactions and torsional amplifications. And this is when the electrical system resonates or exchanges energy with the mechanical frequency of the shaft. And it can produce torque amplifications. So for the positive sequence of the harmonic armature, currents produce rotor subharmonic currents at the frequency FER, which we talked about. Now, for this rotor frequency, in order to interact with the shaft frequency, we need to calculate it. So for our last example, we calculated the rotor frequency. For this, the subharmonic frequency was 36. Now the rotor frequency will be 24. Now if this rotor frequency interacts with the frequency of the shaft, then we're going to amplify that torque. So what happens when you amplify the torque? Well, you can pretty much damage that shaft. So that is the way that this new frequency gets modulated on a new frequency, FEN, and that's calculated FO minus FN. So that's when growing oscillations can occur. And Fn is pretty much the natural frequency of the mechanical system, based on the general mass, low pressure turbine, high pressure turbine, and that's how we calculate the natural frequency of the mechanical system. And this is just an example of how the torque is magnified. So you can see that it increased in a exponentially manner, and that is what can damage the shaft of the generator. So that is pretty much what we talked about, and we know there are various solutions out there, but for our solution we pretty much created a subharmonic relay which detects subharmonic frequencies, minimum and maximum ranges of subharmonic frequencies. And the theory behind subharmonic detection is pretty much calculate your minimum and maximum subharmonic frequencies, and there are three different detector levels: nominal, fundamental, and a total subharmonic distortion detector that we can use in the subharmonic relay. We can calculate from the 5th to the 40th harmonic. I know this graph is not updated. But we can also provide subharmonic tools that will give you oscillographic data, and it would also give you the subharmonic spectrum and the subharmonic currents that are involved in the event. So for the subharmonic current nominal ratio is nothing by calculating the highest subharmonic ratio divided by the nominal current of that relay, and then you calculate a percentage, and then you can base your settings based on this percentage. Here's a screen of how that could be done. And for the subharmonic current, it's a similar fundamental ratio. Instead of using the nominal current, now we use fundamental current, and we use the highest subharmonic seen during the event divided by the fundamental current seen during the event. And that is an example, and the fundamental ratio can be calculated, and you can set that relay that way. We can also calculate the subharmonic distortion, which is nothing by the square root of the currents squared, and you can also calculate that. In similar fashion, the voltage nominal ratio can be calculated, and we take this high subharmonic voltage divided by the nominal voltage level, 69.120, depending on the PT ratio, and also for the fundamental ratio, we take the fundamental voltage in the event and calculate the ratio. That is a screenshot of how that could be done. So that is the subharmonic protection. Now it is this specific relay also comes with overvoltage and overcurrent protection, which we understand why we need overvoltage protection. So it is great to have an overvoltage setting installed and in service, even if you don't have subharmonic protection. This is just a 3-line schematic of how that can be wired, how this relay is applied. And the specifications of this relay, it comes with 4 sets of 3-phase currents. It comes with 2 sets of 3-phase voltages, 9 digital inputs, and about 14 programmable outputs. The real connections for the unit, for the 3U and the 4U unit, and the subharmonic protection functions for this relay. This is how the relay actually looks like, the front panel. It's a brand new platform. It's IEC 6150 ready, so you can use any other relay to control this relay, or you can send signals out of this relay via use messages. Recording, we provide 96 samples per cycle. We do swing recording, just in case your system starts to oscillate. We provide transient and swing recording options as well. We provide a sequence of events, recording in the form of text to tell you what exactly has tripped. And so, as conclusion, we have provided today in this presentation an application of a subharmonic relay, and we have given you the reasons on why you should have a subharmonic relay installed on your system. And if you have any other questions regarding this presentation, please feel free to contact me. You have my information in the first line. I appreciate your attention. Thank you.